introduction, and I would also like to thank Honorable Director and all the organizing committee members who has given me this opportunity to share some of the research experience to all the participants. So to start with, let me share my slides. So I hope the slides are visible. Uh, yeah. So I'll be talking on security analysis of safety critical systems. So first, I would like to emphasize on the importance of this topic so that a motivation can be drawn. And to start with, I will like to discuss about safety critical systems. So safety critical systems are those systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human life. And there are a wide range of applications where we make the use of safety critical applications, for example, in railways, in automobiles, in defense, in medical domain, in nuclear energy, and in aerospace, and so many others. And these safety critical systems are most of the safety critical systems are IoT also in nature, and there are several processing nodes in the same in such systems which are connected with each other. So when a thing is not standalone and it is connecting with any other, definitely there is a possibility of the threat, and which is known as the security threat. So specifically in this session, I'll be discussing how we can quantify some of the security related metrics, especially if you're dealing with the safety critical systems. To start with, let us have a outline of today's outline quickly. So introduction, we will see like what is all about security and what is the essentiality of the security. Then I'll be discussing the security modeling process. So it is so basically once I'm going to implement any aspect, I have to model it. So if I want to incorporate the security in any particular system, I have to model that security process, and that will be implemented thereafter during the implementation phase. And then I'll be discussing a um, Patrinets, which is a mathematical tool. And basically, this Patrinet concept was introduced in 1960s by a German PhD scholar, and he introduced this concept to model the stochastic behavior of the system or the stochastic processes. So, if you want to categorize the types of processes, it can be done into two parts. There could be deterministic process or there could be stochastic process. And deterministic processes are those processes, the outcome of which can be 100% guaranteed. For example, if I do have a pen in my hand, and if it gets slipped or if I drop the pen, I can 100% guarantee it is going to fall down on the earth because of the gravitational force that is acting on it. So here I'm 100% sure about the outcome of this process, and hence it is deterministic in nature. While if you talk about the stochastic processes, these processes are those processes, the outcome of which cannot be 100% guaranteed, in spite of systematic planning or using all the international standards or practices. For example, suppose I do have to attend a meeting in Hyderabad at 4 p.m., and for which I have to fly from Bombay, and considering all the local traffic delays and the flight delay and the local traffic at Hyderabad also, and considering some significant amount of some significant overhead time. Suppose I plan at 12 p.m. from Bombay, but then also I can miss my target, and the reason could be manifold. The reason could be, suppose if I'm going from the routine normal route from my home to airport, and it may be possible when I was about to reach to the airport, uh, which was just 1 kilometer ahead, and there was a road construction that is going on, and road is blocked, and then I may have to take the turn, and the that alternate route is very far, or and there is a lot of traffic also, because the normal route now has been blocked. Or the other reason could be, when I suppose I reach airport on time, but there could be some excessive delay in the flight, or because of some technical or administrative reasons, so there could be flight cancellation as well, which I might have not postulated. So what I mean to say, these processes, in spite of the rigorous planning, the outcome of these process may not be successful. And even if you see, like, the human is also stochastic in nature, because it depends like on the current state of mind. So definitely all the systems that are made or that are developed by the human definitely will be stochastic in nature. So stochastic means it contains some kind of randomness, and randomness is nothing but it is a thing which is unknown to us, which we don't have any prior information. So I'll be discussing the what are the basic building blocks of this battery nets, and what will be the working mechanism of this battery net, and then I'll be taking a case study where I'll be illustrating for security analysis using this battery net, and then I can conclude my session with some doubts clarification. So, uh, software has become an integral part of everyday system, and every day, our lives are based on software. And in early stage, software uh, was not used in the safety critical environments, but as and when we started proving its performance, its reliability, its flexibility, its dependability, so it has become now the major component of this safety critical system as well. But when software comes into the picture, definitely the problem of the security and safety becomes more important, because it may it may be attacked by the by any trait. And already we have talked about the safety critical system. So these are the examples, like railways, airbag, medical system. These are the examples of the safety critical systems. And so digital technologies such as computers, control systems, and data networks, these play a very important role in now almost every kind of systems, and especially if you see, for example, in the nuclear power plant, if you look, so these are the important uh, these are the important components. And but if you see uh, the major accident in the safety critical system that took place just because of the security threat, probably it will give more motivation to think, or to give a serious thought process for devising the security modeling in a robust manner. So if you look some of the accidents in 2003, the enterprise and the control networks of Davis Bessie nuclear power plant that is in US was shut down because of the infection by a slammer bomb. And when any nuclear power plant remains shut down for 24 hours, it is a loss of like million dollar loss. In the same way, in 2006, the instrumentation and control system of Browns Ferry nuclear power plant in U.S. state of Alabama were disabled because of some digital network problem, and therefore the operator has to shut down the nuclear reactor to ensure the safety. And in 2010, a malicious code known as Struckness, which is a very popular uh, kind of virus, and it was found in the Siemens PLC. So it damaged the Natanz nuclear power facility in Iran. So these were some of the important accidents uh, that has taken place because of the cyber attacks. And there are some important quotes also that has been given by the popular personalities, which again motivates us to think about the security aspects. So, according to the Dr. Rajeshwari Pillai Rajagopalam, and she's a senior fellow at Observer Research Foundation, New Delhi, she wrote in her article Nuclear Research in India that one of the more probable threats to Indian nuclear facilities could come in the form of cyber attacks. And the capacity of terrorist groups to use the cyber tool to attack a nuclear installation is far higher as compared to the other attacks. So, as more and more systems rely on the computer networks, cyber attacks have grown to be a major threat to India's nuclear installation. And you might have heard, for example, in India in 2018, there was a cyber attack, external attack in one of the Indian nuclear power plant. Similarly, the Thomas French, who is a senior vice president of reactors and services for Areva, which is a good company, and it is responsible for the construction of nuclear power plant in North America. He said that across the nation, nuclear plants are being licensed to operate for longer periods of life and are transiting from analog to digital systems for increased safety and performance. But while this transition to digital technology is beneficial in many folds, but there is a need to integrate cybersecurity measures. And protecting the US nuclear power infrastructure from exploitation and cyber attacks perpetrated against critical system networks is an industry challenge. So these are the some important quotes basically that has been given by some of the popular personalities, which gives a motivation that we have to model the security process in a systematic manner, because there is no generic security model. It depends on the context of your system. So first, you have to analyze the system, the target system for which you want to propose a security model. And but a generic framework I've been introducing for security modeling. So the framework contains several phases, and in the first phase, that is known as security analysis team. This is a very important phase, and in this phase, uh, basically, suppose I do have a system, and I'm working on that system as an soft project manager, and I want to give the security solution. So first of all, I'll have to hire the security analyst. So basically, I should be uh, I should have a potential uh, to hire the real experts of the real security experts, which can analyze the system properly and give some kind of solutions. So the first thing is we have to uh, hire the security analyst team. Definitely, those team will be the part of the company, but the project manager will float a requirement, and accordingly, it will be the team or the or the members will be assigned to them. Then the next is the consistency of definitions. Now, this is one of the important phase. What does it mean? See, in the security, for example, there are the various terminologies like virus, worms, trojans, and you should not use or misuse these terminologies. There should be a clear, defined, thick line in between these terminologies, because every solution is very costly, and it may be possible because the virus may be having more severity, and that is why the solution provider has to uh, give a serious thought, and it may incur more cost. Then probably the worm, probably if you say, like, if something is uh, if my terminal is connected to the printer, and if I give a command to print something, then definitely if there is some kind of worm or some kind of virus, it doesn't make any much effect with respect to the safety, right? So here I will not be putting more cost in providing the security solution. So the consistency of definition is very important, and it has to be circulated to all the stakeholders. And the third phase is very important. Is it says, like, you have to understand the characteristics of the system. So basically, it is like, if you see, the cyber security is inherited from the physical security. So if you say, if you are in a flat, and you have to understand the characteristics in the flat, you have to see, like, okay, this is a room, here there is a kitchen, there is a bedroom, and in this way you are able to understand, or you are able to analyze your system. Suppose your flat is a system, and which may be a target for this threat. So if you are dealing with the safety critical software system, you have to analyze the characteristics of that particular system in consultation with the system analyst. So I mean, you have to really understand the design so that you can identify the loopholes into that design, right? So in the flat, if I can identify where are the doors, or where are the windows, or where are any other openings, because the security can only be compromised from those openings, right? So I have to understand the openings, or the possible openings in the system as well. And then I have to identify the critical assets and processes. So, for example, a system contains like many modules, and one module is, for example, if you there is a system of ATM, one module is uh, uh, transaction, one module is pin change, one module is print, one module is service request. Then definitely the transaction module is most important, because it should count how much money has been taken, how much money has been transacted, right? So in this way, we have to really analyze uh, yeah. So you have to identify the critical assets and the processes, because you have to put a lot of effort on those critical assets and processes, and you cannot put equal effort to all the assets and all the processes. And then after that, you have to identify the system vulnerabilities. System vulnerabilities means you have to think in what way my system can be compromised. So if I compared with the flat, I'll have to think, yes, these are the openings, doors are the openings, windows are the openings. So the a thief can come only from those openings. If there is a wall, I should not be worried about it. So I'll have to identify the system vulnerabilities, and then I can identify the threats. Now, what could be the possible threats? For example, if one facing of your flat is falling in the near the jungle, then definitely some animals kind of thing can come, or some snake can enter into your home. So the threats you have to identify, and accordingly you have to devise the solution. So after identification of the threats, you have to identify the security goals. Now, what are the security goals? And once you have identified the security goals, you have to generate the threat model basically. And so, threat model means what could be the various threats and how it can compromise your security. And then you have to also consider the risk in case if you are postulating some solution, and in case of failure of that postulation because of some randomness, so you have to do the risk assessment also. This is a very critical phase that you need to do, especially if you are dealing with the safety critical systems where you cannot take it like a normal systems. And then after that, you have to create a document based on these information. You have to create a document of security requirements, so eliciting security requirements, and then you can go for the security modeling. So this is a generic framework which basically tells what are the various phases that can be that or that any system should contain to model the security. Definitely depending on the size of the your system, or depending on the policy of your company, or depending on the system analyst, one or two phases can be compressed to one. So and now let me uh, introduce the concept of Patrinet. So as I said, it is a very good graphical and mathematical tool. And why graphical tool? Because I can simulate my system graphically, and which can be seen by all the stakeholders. And it is a mathematical tool because I can embed the mathematical knowledge, and I can derive some of the state equations or algebraic equations to know more and more insights about the system. So in this session specifically, we will be seeing how the security aspects can be taken care of. So if you look into the history of patronets, starting from the origination, I request you all of you to please mute themselves. Hello, I request you all of you to please mute themselves. Hello.
Dear participants, please mute yourself.
If you don't want to listen, you please mute themselves so that other can listen.
Sorry, sir. Sorry, I have muted him.
Yeah, thank you. So, so the concept was started in 1962 by C.A. Petri, who was a German PhD scholar. And after going through the thesis, as I said, the concept was introduced to model the stochastic behavior of the process. And after going through the thesis, the people started taking interest. And because there was an era where the people were striving to work on the concurrent and parallel systems, so the people were trying to explore this model, whether it can be used for the concurrent systems or the parallel systems. So in 1970s, and in 1970, MIT USA conducted a conference on concurrent systems and parallel computation. And the conclusions were very fruitful. And then I think I'm getting a disturbance. Okay. Yeah. The conclusions were very fruitful, and then in they again decided to meet to give it thought process how to strengthen, whether they are able to strengthen the capabilities of the model. And with this objective in 1975, again MIT USA conducted a conference on Patrinet and related methods. And then it started gaining the popularity in the industries, where industries started hiring the experts and gave training and looking at the industrial demand. Germany started a course on general net theory of processes and systems in 1979. And then uh, the, the people from the different domain also started taking interest whether this PatriNet model will be able to model their particular kind of applications. And with this objective in 1980, the first European workshop on applications and theory of patronets was started in France. And then there are the different flavors that was coming out. uh, Hello, 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 hello.
Yes, sir.
uh, can I ask to mute? Yes, please don't unmute them yourself, please. Yatin Sharma, yeah, please mute themselves. Otherwise, I will not be able to uh, concentrate on my talk. Then the different flavors of the patronage started coming up. For example, if you want to work on the real-time systems, so a specialized patronet known as timed patronets, where you can embed the timing information and it can give the results like on the like with times. So the first international workshop on time patronage was conducted in 1985. And although this is not exhaustive list, but it gives uh, the motivation of this patronet, and what is the importance of patronet starting from its origination to some of the milestone that it has achieved. And if you look into the applications, it can be used in almost all kind of applications. And now let me introduce the basic building blocks and working mechanism of the patronet. So I request all of you to listen very carefully, because if you will skip this slide, I think you will not be able to understand rest of the one. So suppose I want to model a very small chemical reaction. Just I'm taking a very small, example, just to make you understand the working principle of this battery nets. So this reaction is very simple. That is hydrogen plus oxygen that gives water. And I want to model this reaction. And before modeling, first let me explain the basic building blocks. So if you are able to see this figure, this is the patronet figure. And in this, if you are able to see, there are the three big circles, and these three big circles are known as places. So I have represented hydrogen by one place, oxygen by one place, and water by one place. The next building block is the rectangular bar, that is known as transition. So here in this figure, there is only one rectangular bar, and the places can be connected with the transitions, and transitions can be connected with the places, but there cannot be direct connections between the transitions and places. And The connections can be done by the directed and weighted arc. So directed means it is some direction, and weight means it will have some weight. I will tell you the significance of the weight, but if you will see in this figure, the hydrogen place is connected with transition T with an arc having weight 2, and the oxygen place is connected with transition T with an arc having weight 1. Although I have not put the uh, numeric 1 explicitly, so if I don't put the numeric 1 explicitly, by default it will be treated as one weight, or either you can put also a numeric number. And similarly, the weight of the arc connecting the transition T and water place is 2. Then there is a concept of input arc and output arc. So the arc which is terminating on an entity, for that entity, all those arcs are input arc, and from where it is emerging for that entity, those arcs are output arc. For example, in this figure, hydrogen place contains one output arc, oxygen place contains one output arc, transition contains two input arc and one output arc, and oxygen place contains one input arc that is coming from transition T. The next building block is, if you see the small embedded circles inside the place, and these circles are known as tokens, and here I am representing these tokens to represent the atoms. For example, hydrogen contains 2 atoms, so I am using 2 tokens. Oxygen contains 2 atoms, so I am using 2 tokens. And more importantly, the distribution of the token among all the places represent the state of the system. So here, if you see, the distribution of the token is 2, 2, 0, because hydrogen contains 2 tokens, oxygen contains 2 tokens, and water contains 0 tokens. So 2, 2, 0 is the distribution of the token. And then, so it represents the left side of this equation, that is 2H2 plus O2. Now it has to convert into the water. It means it needs to change its state. And as I said, the state is represented by the distribution of the tokens. It means I have to change the distribution of the tokens. But there is a one rule which can change the distribution of the token. And the rule says that at least at least one transition in any Petri net figure must be in enabled state. I repeat, we can change the distribution of the token provided at least one transition in the Petri net is in enabled state. So here, because there is only one transition, so this T must be in enabled state. But what is the enabling criteria of the transition? And the enabling criteria says that all its input places must contain sufficient number of tokens. I repeat, a transition is enabled only and only when all the input places must contain sufficient number of tokens. So with respect to this figure, the input places of the transition T are hydrogen and oxygen, and these two places must contain sufficient number of tokens. Now, who will decide the sufficiency criteria of the tokens? Here, the significance of the weight comes into the picture. So, the weight of the respective arcs will decide the sufficiency criteria of the tokens. So, if you see, the weight of the arc connecting hydrogen place and transition T is 2. So it means hydrogen place must contain at least 2 number of token. And if you see the weight of the arc connecting oxygen place and transition T is 1. So oxygen place must contain at least 1 number of token. So you can see here the sufficiency criteria fulfills and hence the transition T is in enabled condition. And when transition is in enabled condition, it fires. And when it fires, the movement of the token from all the input places to output places occur. But how many tokens will be moved out from the input places and how many will be deposited to the output place will depend again on the respective weight of the arcs, the weight of the respective arcs. So here uh, you can see the weight of the arc connecting hydrogen place and transition T is 2 and oxygen place and transition is 1. So from here the two tokens will be moved out from hydrogen and one token will be moved out from oxygen. And how many will be deposited after firing because this is enabled, and then if transition is enabled it fires. And how many will be deposited to output place? The two tokens will be deposited because the weight of the output arc is 2. So 2 token will be deposited into the water place. So interestingly, we can conclude that there is no law of conservation of tokens, because if you sum up the total number of tokens that have moved out from all the input places is 3, but only 2 tokens are deposited in the output places. And now the state has become like this. So 2 token has been moved out from the hydrogen place and 1 has been moved out from oxygen place and 2 has been deposited into the water place. And so now the state has become 0, 1, 2 because the distribution of the tokens represent the state of the system. So now the state has become 0, 1, 2. So now again you can check the enabling criteria of the transition. You can see it is not enabled at all because all the input places must contain sufficient number of tokens, although oxygen contains, but hydrogen does not contain, which it should contain at least 2 number of tokens. And here I want to introduce the concept of reachability graph. So one interesting thing is it also, this Patrinet uh, figure or the Patrinet model also helps you to identify the state space of the system. What could be the total number of states of that particular system throughout its operational life? So because now it is a dead state, because no transition is enabled and it cannot fire, so no movement of the tokens can take place, and hence it cannot change the state. So reachability graph is nothing. As I said, it is a graph, so it contains nodes and arc, and nodes represents the state of the system, and the arcs represent the transitions which are responsible to change the state of the system. So if you want to draw the reachability graph of this particular example, it will be 220 because 220 is the state of the system. Then transition T will be in arrow and then 012. So this is the reachability graph. Now the preliminary uh, we have already gained the preliminary knowledge about the Patrinet, and now I want to take a case study. Where I will be using the security modeling on that case study. So I'm using a digital feed water control system. So first, let me make you understand this system because it is very important to understand the system, what is all about. So basically, what happens? Sorry, if you are able to see, There is in the leftmost and lower side, there is a reactor which is written. It is elliptical in shape, and here basically all the fission reactions are taking place. And we know like how nuclear reactor works. It is there is nuclear fission, and with the nuclear fission, because every fission generates a almost 220 million electron volt of energy, and some 2 to 3 neutrons, and again these neutrons will strike to the fuel, which is generally of uranium, and then again each neutron will be responsible for one fission reaction, and in one fission reaction I get 220 million electron volt of energy. And in this way it is a kind of chain reaction, and huge amount of energy gets accumulated, and hence it is important to draw this amount of energy, because otherwise your all the instrumentation will be uh, compromised, or the integrity of all the components will be compromised. So what happens here, a lot of heat energy is there, and so there is a reactor coolant pump which is pumping the cool water in a pipe. This arrow is nothing but it is a pipe, and it is going from inside the reactor. Then definitely the heat will be transferred and it will go, and you can see a elliptical dome shaped structure on the top. This is known as a steam generator. And so basically what happens in the steam generator, it contains two logical portions. The lower side is filled with the normal water, and the upper side is empty. And when this hot water, almost more than 300 degrees centigrade, it flows in through the steam generator, this normal water suddenly converts into the steam, and because of the lighter density it gets accumulated on the top portion. And then it is connected to the turbine through the set of valves, and where it can drive the turbine to generate the electricity. And not all the steam can be utilized to drive the turbine, so the unsaturated steam again come back. It will condense from the main condenser, and again it can go into the steam generator. So this secondary loop is keeps on going up. But because this steam generator, inside this there is a water, and it is getting converted into the steam, which is basically utilized to drive the turbine. So this water is level starts diminishing, and hence we have to make up this water sufficiently. So this digital water is nothing. Digital water control system is nothing but actually it maintains the level of the water inside the steam generator, because if there will be less water it will not be able to remove the sufficient or the required is heat from the reactor, right? And so there is external hookup which basically when it sees that the water level is diminishing with from a certain level, it start injecting the water from the external sources, from the external pipe. So here there is a main and backup computers which keeps on monitoring these parameters, and here this is the main feed valve. Uh, so the so it is a feed water pump FP, and it pump the basically the water inside the steam generator. And if in case suppose the main feed valve is not working, there is a backup feed valve. From this we can pump the water into the steam generator. So this is a requirement of the system, and so it's all governed by the computer. And now let us generate a model, basically the Patinet model. And the Patinet model, because it contains the places and transitions. So this is a Patinet model. Let me explain each and every place and transitions. So the first is P0, which basically represent, if there is a token in P0, it represent that feed water system is in ready state. And then there is a T0 transition. It represent that steam generator level deviated from normal limit. And when it is deviated, it means it will trigger. And after trigger, uh, it means it will fire, and then um, definitely the main computer or our backup computer will receive a deviated value, which can be represented by P1. So P1 is a kind of, some activity. And then suppose there could be, then this error value or this deviated value will has to be communicated to the controller, because the controller has to actuate the feed valve, right, accordingly. So this deviated value will be sent to the controller, which is shown by the T1 by triggering the T1. And then the controller receives this error signal value. It's represented by T2. And then there are the two possibilities. See, either there could be some security threat which can influence your value, this error value or this deviated value. So I have considered the two path. One is T3, which represent that controller recognize the failure of the computer, means computer has been influenced by some virus. So it means it will not then actuate the actuator, rather it will send the previous correct values or the freezed value to the actuator device. And T4 is controller does not recognize the failure and send the false value. So it fails to recognize that there is some deviation or there is some attack. If it fails, then definitely it will send a false value to actuate the device. And then the P3 means it actuate the actuator according to the information that it receives. And then T5 means, okay, we can reset the system. And T6, there is a possibility then actuator can stuck in between also. If I'm trying, because of some mechanical failure, if I'm trying to open the wall, but it got stuck to open, then definitely I'll have to change the state. Activity will be the actuator in a stuck state, and T7 will represent the repair of that state. So this is the entire model basically, and now I want to compute the security threats. Right. So yeah. So basically the structural properties. We can now analyze the structural properties and behavioral properties of this battery net. And structural properties are depending on the topological structure of the net, namely P variant and ciphers. So P variant basically corresponds to a set of places whose weighted count, weighted token count is constant for all reachable marking. Now, what we need to do to quantify the security matrix. So first we have to calculate the P invariant. Okay, so P invariant I have already told corresponds to set of the places whose weighted token count is constant for any reachable marking. Marking is nothing but distribution of the token, that is state. Okay, and reachable states means we see like whether from one state I can be able to reach to the another state. So I have to calculate first the incidence matrix with the formula, that is A is equal to D minus D plus. Now let us see what D minus is. D minus represents like how many arcs are basically terminating from the particular to the particular place. For example, if you go back in this, from P0, to P0, it is coming from T5 and T7, right? So from P0, it is coming from T5 and T7. So how many arcs are terminating to all the places? From which transitions? For example, the, let us see about the P1. So P1, the input arc is coming from T0. So just fill in this metric element with 1 and put rest of the zeros. And in this way, we have to construct the D minus matrix, and D plus will be how many are emerging from the particular places. So going back from the P0, it is emerging to T0. So from P0, it is emerging to P0, and we have to keep rest of the values as 0. And similarly, we can construct the D plus. So basically, if you see the logically what it is doing, it is just seeing like how many things have been entered and how many things have been gone out. And the concept I tell you how it comes. For example, if there is a bank, then you can keep on counting how many customers in a day has come in and how many customers in a day come out. And there should be the difference should be 0. If there is some difference, it means there is some internal trait, right? So in this, so this is the way basically we are trying to do that, and then we can calculate the A matrix, that is known as the incidence matrix, after subtracting these two matrices. And now we have to calculate the P invariant. So what we have to do, we have to just keep this matrix as it is, and just write some adjacent diagonal matrix, identity diagonal matrix, or unit diagonal matrix, having the same number of rows like this incident matrix have, and it should be the square matrix. So here you can see like 5 rows are there, so 5 by 5 I have made a unit diagonal matrix. And then you have to perform the calculations in such a way that you have to turn up this incidence matrix into the 0, because ultimately our aim is we have to make it this matrix 0. How many comes out and how many go out, how many comes in and how many go out. And then you have to analyze what is the balance, what is left out, or what is the transformation of this unit diagonal matrix. And we can see like if there is one like here, this is the row identity matrix. So if any column or if any element of this row would have been 0, it would have been deadlock. There is some glitch. So that is why now there is no security trait, no security traits. So basically it ensures the liveness, and it checks basically some deadlock is not there or not. And similarly, just for the double check, we have to calculate the T invariant also. And in the T invariant, we have to look with respect to the transitions, right? Here we had made with respect to the like places. So what you have to do, you just write this incidence matrix and just swap the rows and the columns. Just take the inverse of that, right? And this is we have swapped the rows and columns, and now again keep row identity diagonal matrix of the same number of rows like it is having, and then you can keep on applying some operations in this matrix so that I can get the zeros. And now you have to analyze the transformation of this unit diagonal matrix. And then you can see like every row is known as T invariant. So this is Y1, for example, first row. This is second row. This is third row, and I'll have to analyze each and every row. So here, if you we can see like there must be at least one in any element. Then we can see like okay, there is no deadlock or there is no dead state in there. So it means any state cannot be compromised. So this is the way like basically we can perform, we can quantify the security metrics, and some of the behavioral analysis can also be performed. For example, the properties that are important and that can represent the security basically metrics. One is the reachability, so it determines whether the given state or the marking can be reached from the initial marking through the sequential set of transitions. The coverability, it determines whether the specific marking. So coverability means whether one uh, state can be reached or whether any specific state can be reached or not. If any specific state cannot be reached, it means it is some dangerous state. It may be influenced by something. So, so it determines whether a specific marking of the patrinet can be reached, and this property is used instead of reachability in the cases where we need to determine whether the system can be compromised in a specific way. Then we can check for the boundedness. Boundedness means there should be uh, there should not be inconsistencies in the token distribution of among the places. It means it should not happen like one place is getting more and more and more token after every iteration. It means some additional information is coming, and either yours there is some design system design, or definitely there is a cyber attack. So this property is useful in analyzing multiple concurrent attacks, and places that accumulate tokens can be identified and flagged as critical. So the patrinet model is of a single attack is safe and bounded as one token exists in the net. And we should always try to design the patrinet model so that at a time one place should not contain more than one token, and it is known as one boundedness. We can check for the reversibility property, which basically identifies the transitions that will never be able to fire, indicates that some corresponding exploit is infeasible. Conversely, a live transition can always fire, such as significant vulnerabilities. Then repeatability property, it does not supply additional information to the defender, and this property, however, like that, therefore it is of limited use in security analysis. And persistence is an important property which determines whether a marking exists or a state exists where a transition is disabled because of firing of any other transition. And this information will be beneficial in determining the ways to prevent or stop an attack. Then the consistency, it determines the transitions that are not possible at all, and this could aid in decisions regarding the defensive measures. Similarly, the conservation, it is indicative of a net that creates more tokens that are consumed. So beneficial for the analysis of multiple concurrent attacks. Similarly, the synchronic distance is very important. It tells like how much time it will take from one place to another stake. It means if the attack has happened, I can able to analyze like how much time it will take to come to me, so that by that time I can take some preventive action or preventive measures. So that's all I wanted to conclude. In conclusions, like software security is a key part in the software quality, and software security, although the improvement is hard, and there is no generic models. So, and the system analyst has to take a role. We have to analyze the attributes of the system, and like the way I had pointed out during the explanation of the security framework, what are the various phases. So basically, definitely all those phases uh, should be taken, should be considered, but depending on the context of the system, the activities has to be customized, and the measurement is a very important for finding the correct model, and we can see like how the patrinet can be used for the security analysis. And these are some of the bibliographies which an interested person can go through. So that's all I wanted to discuss. In case of any questions, I'll be happy to answer.